So, I hope everything is going to be all right now. Sorry about that. So, today we are going to continue our talk about the topic of decentralized and anonymous governance with our good friends at Devote and at Gosh. We already had a couple of sessions before with Eugene Morozov, with Mitya Grashevsky. We had a wonderful talk during our Blockchain Community Day conference from the past 2 years, and we had a good talk about understanding decentralized voting. So now this topic becomes a series of events, and I'm very happy to invite our today's guests once again on this stage. So hi everyone, hi Eugene, hi Mitya, how are you?
Hello and good afternoon.
Great, thanks. How are you?
Yeah, thank you for being with us today. And without further ado, I'd like to ask you to say a couple of updates, maybe some news about what has happened throughout the past couple of years. And after that, we can start with the presentation. So
Yes,
the
Alex,
floor is
thank
yours.
you. Thank you very much for the opportunity to come back. This has become indeed a very good tradition where we come and report to your audience the latest news and developments that are happening in our community. You may recall that we started more than 2 years ago with a description of how our community responded to an article published by researchers at Massachusetts Institute of Technology and Harvard, criticizing the use of blockchain in elections. So our community rallied against that and came up with funding to start Devote as a project. And we talked about this amazing community power. Now, then we talked about what is happening in public election space globally. We talked about a huge problem that exists today everywhere without exception, and that is doubt in election results. So this is a problem that Devote was originally designed to create. But then we realized that there's actually much broader potential use for the software. And one of the directions that we're going into is more broader governance, more general governance issues that are relevant, not just in the political or public area, but everywhere, including commercial companies, including decentralized organizations, nonprofits, universities, you name it. Basically, we realize that the solution is needed in many, many, many places. And so we started on the road to adoption. Now, there are a number of important developments that happened, as you said, Alec, recently since we started. And we'll talk about that in detail later today. But one of them I'd like to mention is this. There's really two ways to adoption of new technology that is generally known. One is bottom up, where we come to small teams, you come to individuals, and they see the value in something they're looking at, and they start using it in their daily work, starting small and then wider, more people joining, etc. And there's that's a very legitimate way for adoption, and many projects are successfully being adopted in this way. We tried, in addition to that, we tried a different approach, and that approach is from top down. We actually approached an organization called the United Nations Internet Governance Forum Dynamic Coalition on Blockchain Assurances and Standardization. This is about as high as it gets. This dynamic coalition is part of a broader United Nations. It's not, of course, the UN General Assembly. It's one of the sponsored organizations by the United Nations. But nevertheless, a significant progress that took place is a decision of the first such organization in the history of United Nations to form their own DAO and to work as a DAO, including conducting their own voting, their own elections, including. And that process is happening as we speak right now. In fact, that group, the Dynamic Coalition, is now developing its own bylaws or charter, which would reflect how the new technology developed only very recent years can be the backbone, the foundation, essentially, of decentralized work by many top-level organizations. So I'm pleased to report that United Nations Dynamic Coalition, this is the first one of many that they have, is working on a weekly basis now to build their stuff on Gosh, and the vote is included as an anonymous voting option into that process. So I'm very pleased to report overall that adoption of this brand new technology is on the way globally. We are working with a number of very active specialists and experts in this field. There are approximately 140 members of this dynamic coalition. Roughly half of them is active, and many already joined the DAO that was formed by us and are starting the first, let's call them baby steps in their understanding and learning the usage of this brand new technology. So that is primarily what news we had. We also participated in a number of government tenders. Remember, we started with the public space with political elections. So we participated in a number of government tenders. We didn't win any first places yet, but we came second in a very large national election, which is extremely encouraging. People there understood and appreciated the value that this new technology brings. And yeah, we didn't win because we didn't have all the documentation and external independent references and opinions and previous government contracts. That's all coming. But bottom line is we are now in the mainstream tendering process in several jurisdictions, and that's very helpful. Now, today we're going to talk about something different. Not public or political elections, but how governance in DAOs actually may work. There are numerous questions related to, of course, how DAOs are functioning today, including in legal area, including in historical issues, including in practical implementation of any real-life solution. But today we want to talk about something very, very promising and very successful. And that is inclusion of anonymous voting into a much broader governance process. And with that, I'd like to introduce my good friend and colleague, and also Chief Executive Officer of Gosh Operating Company, Mitya Goroshevsky, who is also a Chief Architect of several blockchains, starting with our original Everscale, and now Gosh, Akinaki, and so on and so forth. Mitya, the floor is yours. Thank you.
Yeah, thank you, Eugene. Yeah, I don't think like my talk today, which is called, and we can put maybe slides on, which is called Consensus from Machines to Humans. I would like today to put this whole thing into perspective, because like we hear a lot of different names around DAOs, around blockchain protocols, around blockchain consensus protocols, and around some other consensus protocols. And I don't think there is a clarity, at least from what the communications that I get. There is no clarity on the context of all of that, how that's all relates to each other. Is there a kind of a unified system for all of that? And I think it's very important to put that into context before we kind of start jumping and saying, like, let's use DAO, let's use blockchain in elections. Let's talk about the blockchain itself and how this whole thing relates one to another, okay? So that will be quite controversial speech, you will see. It won't give you all the answers. I would also ask you to kind of drop in chat any questions you might have, or if you kind of don't understand anything, meaning that the talk is quite technical, actually, at parts. Yeah, I will try to keep it as human as possible, but yeah. So we start with machines. They start with the computer consensus. So what is consensus in computer science? It's some computers, distributed computers, agree on some state of things, a common state of things, somehow, right? And that need to take into account that this is quite unstable because some of them may get lonely and crash. I don't know. So some of them may just fault. And we call these faults like Byzantine faults. Sometimes these faults just a crash faults, and there are whole, I would say, whole theory in the computer science behind the crash faults consensus algorithms, but they also can have a malicious faults. And then we have a different set of algorithms that we mostly will talk about. So in crash faults, you have like algorithms like 2PC, 3PC, which are basically just simple agreement algorithms, between several machines. Like you select a leader pass a message to other machines reply, and they updated the state, and it seems to work, but it's until it doesn't. It doesn't because there is some blocking in this algorithm apparently, and then they created 3PC algorithm, which is pre-commit algorithm there as one of the steps to kind of try to avoid the blocking, unsuccessfully so. And then obviously Les Lamport came with Paxos. There is a VCR also, which is important. I'm not going to go deep into that, but bottom line, it's a family of computer consensus algorithms, which are mostly related to the problem where you have computers in, for example, database clusters in the data center, and you need them to agree on some state so they can crash, and there may be network failures and stuff like that, right? But then we had a problem that you can have some network of these distributed computers, and you would like this network to agree on a common state, but you may not control the network. And in this case, there are some malicious faults that can be presented. And the first algorithm that actually tackled that problem, and particularly double spend problem in the context of value transfer, which we call cryptocurrency today, is a Nakamoto consensus. Now, Nakamoto consensus is a probabilistic consensus. So, and we will talk about that a lot today. Probabilistic consensus means there is some probability that it may be attacked, or maybe it may produce the wrong, like double spend, for example. But this probability is whatever low is acceptable to network participants, right? So this consensus protocol for Byzantine faults and malicious faults in particular. In parallel with that, or even before that, there was a BFT consensus algorithm presented. And in particular, practical BFT consensus was presented. And practical BFT consensus says basically that we can agree on a common state with a malicious node presented in the network in a deterministic fashion. So there is apparently there are kind of two families of algorithms in this malicious paradigm, where one is probabilistic, like Nakamoto, and another is let's say deterministic. We'll talk about that, how deterministic is. And then we will talk about some modern consensus algorithms just as a first step. That's not the whole talk, okay, because I didn't want to spoil. So that's the first part, okay. So let's talk about Nakamoto. And formulas are just because they're beautiful. No, I'm just kidding. But I'm not going through the formulas today. And just you can go and check them on in the literature. But basically, the Nakamoto consensus is a probabilistic consensus based on proof of work. The proof of work is a system where, like, the miners trying to win the slot to propose a new block, and if they propose a new block, they get reward for it. So they kind of are motivated to use the hash power of their computer to solve this cryptographic puzzle that will give them the right to propose the block. Now, because this proposal costs a lot of money, they presumably will not try to corrupt the network in their block. So they would not try to present a malicious transaction in this block. Please write me if you know all of that, and I can skip that. But basically, it's providing a security, but security is probabilistic, and there is a probability of the double spend attack in Bitcoin, well researched and defined. Let's talk about this other family, the BFT-based family consensus, deterministic consensus, That means that basically the whole protocol has only two states, one faulty and or not, like 0 or 1. It cannot provide some message that could be that or this, an undecided state. If this system produces the block with the signatures, the correct signatures, 2/3 of the nodes are signing, then this block is final, and we cannot change it later on. Can be perceived as wrong. Okay, that's the assumption. And of course, we can derive from that the probability of attack in the Bitcoin, which will be the probability of the malicious actor to actually own 2/3 of the node for safety, or 1/3 of the node for liveness. Liveness means that the network will continue to produce, well, in this case, blocks, right? So if the 1/3 of the nodes in the BFT network faults completely, the network stops. If 2/3, then the network can be corrupted. These are the assumptions. Okay, but a lot of software engineers, when they hear about BFT, they say, "Oh, that's it, we solved it. That's just ideal, because what else do you need? You have a deterministic protocol, right?" Well, let's examine how deterministic is that. As a protocol itself, it's quite deterministic, right? If you just take this protocol. But when you start to implement it as a system, and that's kind of a computer system, for example, blockchain, then in the context of the broader system is nowhere near to be deterministic. Why? Because for once, it relies on cryptography, on the public key cryptography. And public key cryptography, there is a deterministic encryption schemes for public key cryptography, but actually they are not very safe. They leak the meta information, which then can be quite easily, not easily, but quite easily broken, even by brute force or dictionary attack, for example. So in all public key cryptography, we actually use probabilistic encryption schemes and probabilistic signatures and stuff like that. So the probability of the attack on SHA-256 is that, like it's 256, right? So there is a probability there, and so we can say that all BFT consensus protocols inside the working cryptography system, at least that are probabilistic. So there are no deterministic. So let's briefly come over what we kind of state of mind of today's modern computer consensus protocols. So we have Solana, which you all probably heard about, which is quite fast, claims to be the fastest. It is actually going back. It's like folding back in safety to BFT. There is a BFT inside Solana. And then there is optimization kind of protocol, which is called proof of history, which basically trying to optimize finality to give it to make it shorter. But it has some problems, and these problems being documented in the literature. There are claims of not to being too scientifically correct. Okay, let's put it this way. I'm not going to go through that whole argument. And there are some protocols like TON and Aptos, and they are basically BFT protocols, really. They try to optimize the message complexity of BFT. We'll talk about that in a second. But basically, they're all folding back to BFT. And TON, of course, is completely BFT. It's actually worse than that. It's twice BFT, because there is a BFT consensus inside the shard in TON, and then there is a BFT consensus in the master chain. And actually, they are not really connected. They're not verify each other. So there is actually quite not optimal in terms of the design. But then there are three others that I want to touch upon, which are non-BFT, real probabilistic modern consensus algorithms. One of them is Avalanche, quite interesting. It's voting of a small randomly selected group of validators nodes. So basically, we try to minimize the committee of the nodes that need to participate in the consensus to make it faster, right? To make it faster. So we have, in that respect, we have to deal with two things, like the assumptions of safety guarantees that this kind of probabilistic protocol provides, and with the message complexity, what it basically gains in message complexity. And in terms of Avalanche, the attack probabilities are dynamically changed, which means that you can change the parameters of the network. to be such that the attack probability will just shrink, right? But of course, you pay with that some other stuff. Like, for example, you will need to select more nodes, which increase the traffic and you decrease the throughput and increase the finality time. The finality time is the time between the message and the finalization of that message inside the block, which cannot be changed later on. So this is the assumption of the message complexity. Avalanche is quite good. It's better than BFT. Okay, but it's still, the finality is still not very, very fast. It's still seconds. Okay. Then we have the Algorand, which is another example of kind of subset of groups. It's a 3-steps protocol. And it relies on randomness computation from the previous block to select committee of leaders that will propose blocks. And then the validators of each round will be like, okay, if you have sufficient number of them inside the committee, then okay, then you kind of probably with overwhelming probability is okay, again, probabilistically. Now, the Algorand inside the committee has a BFT again. And that means that the BFT message complexity is there. Now, and that the message complexity is what it is. It's mentioned here on the slide. It's quite problematic in terms of finality, because in the original paper, the finality was like 30 seconds, which is very, very long. But then there was some improvements on that. So that was improved a little bit. It's still kind of problematic in terms of finality times. Then, and the last one is Tfinity. Before I go to the protocol that we're working on, is Tfinity is supposed to trying to build a world computer, so they had to be very fast and quite secure. So again, is a layered protocol, random beacon-based probabilistic leader selection, and then there is some kind of notary layer which finalize the block, provide the finalization, that kind of gadget. There is the main security, that is this. Not going to analyze it right now. Again, in all of this, the probability is quite low. It's like very low, okay, in all of these algorithms. Now, the message complexity, though, is like cubic, and with some modification for adaptive adversary against a static or like mildly adaptive adversary is like quadratic. So again, not ideal in terms of message complexity. But the important thing about all of these protocols is basically, again, it's a probability. We want to achieve the low probability of the attack while try to improve on kind of deterministic algorithms in terms of message complexity. That's what it is. And then I'll just briefly talk about our algorithm, which is Aki-Naki. Is we took the probabilistic message complexity to the extreme. Basically, we wanted to have the absolute minimum of the messages that you can think about. It's quite simple, actually, algorithm. Surprisingly, it actually works. It just has 2 messages. Actually 3 types of messages, but 2 of them are executed simultaneously. So in terms of time frame, it's just 2 messages on the network. It reaches finality is less than a second, and the probability of attack is linear. So it's not quadratic. That's what we really worked on towards, and this is the probability on the screen. Now, so coming back to all that, just to summarize, in terms of the probabilistic safety guarantee, we said that even deterministic protocols are still probabilistic in nature once they are put in the context of real system, like cryptography system, for example. And so we took the SHA-256 probability of the attack. Remember that number? It's here. And we simulated the Aki-Naki probabilistic consensus protocol in terms of what kind of assumptions we would need to take on the network. So the probability of attack would be that of the attack on SHA-256. We took the 1,000 nodes, 800 attestation we need. It's just basically the hash of a block that they prove that the network, 80% of the network received the block. If we have 80% of the network attestation, then even with the assumption of 49% of malicious nodes, which is better than BFT, we can arrive at the same probability of the attack, which is extremely low, basically close to zero. Okay, so we cleared that. I did it as fast as I could. So this is an overview of the computer consensus algorithms. And we can most of the time in computer science, we stop just here and we say, this is good enough. This is a blockchain. Well, then what are we talking about when we say that? Proof of stake. What does that mean? What even it's doing here? Like how it relates to everything else. All right. Is the proof of stake a consensus algorithm? Because we see it all the time in the literal. People just interchangeably use, like, this consensus protocol is proof of stake, and that consensus protocol is proof of work, and that consensus protocol is BFT, how it's all related to each other, okay? Well, in a way, it's not. But proof of stake is a different layer. And some claims can be made even that it's not a consensus algorithm whatsoever. So I will give you my definition of proof of stake. Proof of stake is not a computer consensus algorithm, but rather a mechanism to prevent malicious computer owners to try to tamper with the code of the node participating in a consensus algorithm. I know maybe it sounds like funny, but that's what it is. Because in proof of stake, you take the stake as a person, like to buy the stake in the particular blockchain network. And you provide the stake as a guarantee that the node that you own, or actually sometimes the node that you even not own, if you delegate this proof of stake, but you say, I will bet my stake that this node will not provide any malicious, like not break maliciously the protocol rules. All right. So I put my money on it. Now, when you put your money on that, this is not a consensus, or at least it's not a computer consensus whatsoever, right? It's just you basically guarantee that that you or will not tamper with this node code to provide malicious, behavior, or you will not allow some adversary to, attack your node. You will secure your node. You will hold it dearly, so no one attacks that and no one changes the protocol, and you bet your money on it. Okay. So you sign on this kind of participation law, the agreement. So you will not tamper the code. Is it some kind of consensus? And if it is a consensus, then is there any theory governing this consensus? So I claim this is a consensus because it's not one party who is doing that. We are in this system, a decentralized system. There are many parties coming with their stakes and putting their stakes, and they sign this kind of law, which is a protocol law, by saying, okay, here's my stake. I sign it cryptographically that you can take the stake if I behave maliciously. Now, this is an agreement between several parties, decentralized agreement with the several parties, unrelated parties. So it's a consensus. We kind of signed the law, and this law is becoming our joint decision to join the protocol and to obey by its rules. This is a consensus. By definition, it's a social construct. It's a social consensus. Is there a theory behind that consensus? Apparently, this theory not only exists, is very, very, very old. And the first documented consensus, the first documented social consensus is Ephor's election in Sparta, 754 BC. Okay, so it's quite long. Now, but the theory is a little bit younger, but also very, very long, like the very old. Like the Wikipedia quotes Raymond Lull, 1299 publication on the first social theory rules in description. And then there is a range of a lot of theorems, what they call it theorems, around the social choice theory, what it's called. Okay, and starting from the famous Arrow's impossibility theorem, and then Gibbard, Schatten-White, and Condorcet jury theorem, and so on and so forth. I actually made a list Don't be frightened. I'm not expecting you to read that, but I'm just on the upper side, there are different voting systems created throughout the history, right? To try to tackle what in social choice theory called paradoxes. And there are two types of these paradoxes: simple paradoxes, conditional paradoxes. And you can see I just wrote it, the Condorcet paradox from 1785. Okay, the first description by Condorcet. And then, so it's a long history. What you can maybe see in this slide is that none of the proposed election, none of the proposed voting systems are actually tackling all the paradoxes. So despite all this theory, we don't have a solution for all of the paradoxes of this of the social choice theory, which is quite fascinating if you think about that. So coming back to proof of stake, there is a lot of arguments and a lot of talks when you talk about proof of stake and this social consensus, which goes around, cannot be attributed to the game theory. Because there is another theory that basically says if we're talking about money and the rational choice, then we can say this is a game, and is that a game? Then the game can be like we can theorize about this with the game theory instead of social choice theory. Well, I say no, because okay, let's consider it's not Nash. That's quite interesting argument. A lot of people in blockchain will tell you it's kind of under in the game theory Nash equilibrium kind of thing. I claim it's not, because of we can imagine two network protocols where you have stake in both of them, but acting in one of them irrationally would still be a rational choice for acting on both of them together. Think of that as if there exists a decentralized exchange on one of the networks, which bet on another network token price go down, shorting, right? So you can participate in both. You can short on one protocol, the other network, and then corrupt the other network, even pay the price, and which will be irrational in terms of the decision for this particular network. But because you gain much more on the other network by shorting this first network, you kind of can imagine a situation where you will gain. So you will have to have then the Nash equilibrium apply for both of this system, which is practically impossible, because you just cannot constrain that system into one. Right? There's just infinite amount of systems that can be imagined like that. And it's not cooperative. The Nash requires it to be non-cooperative game theory. Then there is another type of games which is cooperative games, but it's not cooperative, because in cooperative games you need to coordinate with all the parties in cooperative game, and you need to trust, and you need to have a bound agreement in that. So that violates both. Like you don't have an agreement in decentralization, you don't have agreement and you don't trust. So because of that, I think the proof of stake network participation still falls under social choice theory, which basically falls under all the elections and all the choices we make in a kind of social consensus. And all the theory which I mentioned before applies. And so we come to DAO, because this is the instrument that our industry chosen as a governance mechanism for all of the below things. And the below things are the actual protocols, right? So you can govern inside the protocol, you can govern whatever you want, but the rules of the DAO decision making are the social choice rules. Now, there is a lot of questions regarding that. If everything is governed by the social choice rules and the consensus between the machine is basically just a technical part on top of which the social construct exists, then I have a lot of questions towards the social construct. We all should, right? And we all have. And we see the struggle about actually that in the context of, for example, Security and Exchange Commission. And just something that comes to mind. We see that struggle, we see the struggle when we try to apply the DAO rules on the governance processes in such bodies like United Nations Governance, Internet Governance Forum, Dynamic Coalitions, and stuff like that. Every time we try to apply this governance framework to some kind of a process, a lot of questions arises. But what I'm saying is that because the importance of that goes down to the security of the all the networks, including the blockchain themselves, as we just said, that they are governed through the proof of stake, they are governed by this also the same social choice rules. The question of DAO becomes the existential question for the whole thing, including the blockchains themselves. Right? Everything basically is affected. And when we talk about the consensus, we're not supposed to talk about the, computer science consensus definitions. These are very basic technical layer, but we need to talk about social choice theory and the consensus around using this kind of theory, right? So just few questions, and I don't have answers to them right now, and we're not going to there is last slide, okay? Is any democratic process can be seen as a consensus decision making? That's we had a debate about that. So if you have an election, right, and general election in a country, is that a consensus? Because half people may not choose this leader, right? They don't like it. They completely oppose it. They voted for someone else, but they still have this leader as a country president. Are they under consensus? I say yes, because when you decided to be part of that country by decision or by not living, okay, by not denouncing its citizenship, you agreed to be bound by the laws of this country. And as such, you're bound by the consensus, meaning that if the law of this country means that this president will be chosen by this mechanism, even if you voted no or didn't vote at all, you still participated in this consensus by law, by the definition of law, by you accepting the whole construct of law in this country. So you actually, it is your president, meaning you agreed to it, even if you didn't vote for it. Okay? So I think this is important. And actually, if we talk about law, that is exactly what happened when, for the first time, SEC sued a DAO, and it sued another California law. And applying the California law, the court concluded that a group of two or more persons joined by mutual consent for a common lawful purpose, and that is the function of the common name under circumstances for fairness required to group to be recognized as a legal entity. Meaning that even if you didn't participate in the voting in the DAO, in this particular case, Owoki DAO, I don't know what they did, it doesn't matter, you're still bound by the laws of the DAO because you participate in the DAO. And because of that, you're bound by the outcome of the legal procedures against this DAO. And the DAO falls under legal jurisdiction of this particular California court because it's under Opinion 913, under unincorporated association law of California. So in California, there is a law apparently that you can be regarded as a legal entity even without any kind of a corporation, right? But just by association. Is there association? Yes, you're part of the DAO. Is there a decision process? Yes, DAO decide on something. Did you participate in decision? Who cares? Nobody cares. You participate in a DAO, you're bound by the law. That's it. Same thing goes to the presidency in this respect, going back, right? So it means that if you validate the network in a proof of stake setting, you put your stake in the network, you are liable under the social consensus choice that you made participation in this network bound by the network protocol rules. Very interesting topic, right? A lot to think about. So is there a specific theory for the DAO? And no, there is not. And I read a lot about that, did the research, and I didn't find kind of the theory that would be that I would say would be kind of a theory of a DAO. There are a lot of thoughts, a lot of kind of even scientific research around that, but there is no theory, a complete theory of a DAO framework right now. We are working on it, obviously, because we believe it's as you hopefully you saw that as well, that is a hugely important. It's some kind of consensus algorithm which we are all running when we are running or participating in a blockchain, which we don't know the theory behind. I think for that I would like to conclude here and switch to Eugen. Maybe he will going to talk about elections from here.
Yes, Mitya, thank you very much. A lot of food for thought for the viewers. I would like to add just a couple of things to that we're now thinking about practical use cases and implementations of the wonderful advances in science and in technology, some of which Mitya described, which only came very recently. So sometimes indeed it happens that practice is ahead of theory. So first something is created and then it's placed sort of in a broader context to be better understood by scientists. And I think that's what we're witnessing today. So yes, those use cases now spreading across the globe. We generally approach this from the following perspective. We look at public actions, public elections. We look at private situations like in corporations. And then now, as Mitya illustrated today very well, we're also looking at the use of truly anonymous voting in DAOs. Now, just to give you some illustration as to what is potentially possible using the mechanism that Mitya just described, we're talking about a massive potential use of this in a variety of industries, starting with public health research data publishing, or using decentralized Git as a software supply chain security mechanism, or ensuring anonymous peer reviews in research and in science, polling on a massive scale, and then ultimately elections of political leaders, again, cryptographically on a massive scale. So I think in the coming years, we will see adoption of this technology, and those of you who will join us in our efforts to popularize, to educate the potential user base about what is available today, what we internally call the art of the possible, we would very much welcome everyone's participation. There's a lot of resistance ahead of us. I think jointly we can help overcome. Alec, we probably open now for any questions from the audience, please.
Yes, thanks. And let me just open the live chat. Just a second. The first question comes from Alexander Tesler. He asks, hi, could we compare consensus algorithms, POW and POS, between each other in terms of hack probability?
That's for me.
Yes, of course we can. Again, proof of stake is not a consensus algorithm. As I just described, it's a higher level social agreement on top of the computer consensus algorithm. Proof of stake is also not a computer. It's a part of Nakamoto consensus, which is the leader selection kind of part of the Nakamoto consensus, which provides some safety guarantees. It's provide a basis for the consensus, but it's not a full consensus. So both of the statements are not correct. Not proof of work and not non-proof of stake are consensus algorithms. So can we compare between them? In a way we can, for the guarantees that they provide. The proof of work provides the guarantee that because you spend some money on electricity. Without that, the proof of work would not guarantee anything, right? So in that case, you kind of have some money behind it in a real term because you paid electricity. In proof of stake, you also put money in a different way. You just take the money and put them and lock them. So in that respect, both of these mechanisms can be compared as like providing a monetary guarantee that you are a good actor in a way, personally, like the owner of the node. But it's not a computer consensus algorithms by themselves.
Okay. And next question, is that for free?
What is?
I believe the question was asked when you've been talking about Gosh, or
Yes, Gosh is for free. Yes, the usage of Gosh is for free.
and
There is
then
no gas payment. There is no gas payment. Yeah, I didn't touch upon that. There is no gas payment because the Akinaki consensus is so scalable that we can provide kind of freemium business model based blockchain, which I believe is what need to be done for the blockchain to be really adopted. It should be comparable in usage to services the user is so used to, like, for example, like Google services or any other cloud-based services. So yeah, it is free.
Okay. And maybe you have any kind of paid features as for now?
We don't have any paid features for now, but they're coming from different partners who provide services on top of Gosh. They may charge for these services, and in this respect, they will pay something to Gosh for facilitating that. But
As an example, the true anonymity of Devote will be offered as part of Gosh options. So if a user must, for whatever reason, ensure 100% true anonymity, then there will be a small fee for using the Devote as part of Gosh. Mitya, I also was hoping that maybe you will talk very briefly about the Git functionality, because it's probably also relevant with respect to the software supply chain security as a very important component.
Of course, Gosh itself is primarily Git on-chain implementation, and it's kind of a layer on top of Akinaki consensus, which provides additional possibility for governing all sorts of processes. So we use Git, but not just for software, but also for any kind of documents or any kind of processes you want to decentralize. For example, peer review in decentralized science, like issuance of eco credits. Again, because there is in the issuance process, there is a peer review process and so on that you can build on top of Git on chain on Gosh. That's what it is.
Okay. And the next question, is it possible to run any smart contract on Gosh?
Yes, Gosh, of course. So otherwise, how would we implement Git? It's all smart contracts. Is a fully smart contract platform. It uses Tone virtual machine simply because this is the only available asynchronous virtual machine, and we need asynchronicity because the Akinaki consensus is multi-threaded, multi-sharded, so it doesn't make a lot of sense to run it synchronously like on EVM.
Okay, and the next question, what are the key barriers or challenges to widespread adoption of decentralized governance solutions, and how can they be overcome?
Let me start maybe answering this one. There are massive barriers in the public election space. Not everybody wants fair elections, and that is the reason why. What can be done about it? And in fact, what is being done? First and foremost, education. We are trying to work through a variety of higher education institutions to introduce new courses that would explain to people what technology made possible in terms of decentralized governance. Right? Not a lot of people in the world today know what blockchain is, let alone what the possibility is it can open in various use cases. So education first and foremost. Second, you have to be active and you have to join the processes of elections in many different locations, hoping that sooner or later smaller jurisdictions perhaps would adopt this new technology, and then larger ones will take a notice and follow. And then also what I described in the very beginning, the top-down approach. What we're trying to do is to have like UN at large, after the pilot we're doing now in a particular dynamic coalition. After that, we're hoping that the larger organizations within the UN and then ultimately the UN itself, the General Assembly, will use this, and that will certainly go miles towards global adoption, because a lot of smaller countries are looking up to the UN to see what they're doing, what technology is being introduced in the world, what are the risks they're facing. And obviously, if UN does it, a lot of people will follow suit. So thank you for this great question. I think those would be the answers. Miti, do you have anything to add?
Yeah, I agree. There is a lot of adoption barriers in corporate world and in governments and so on. But the blockchain space proved, at least today, it's kind of vividly proved its resilience towards any kind of trial to hamper its growth. It just doesn't work. We will prevail for sure. Even if you think it's all impossible, it will all be blocked. And I don't know what it will, but it won't in the end. Like this will happen. It's coming, to your town soon. And it depends on us. The more we use it, nobody can stop it. Like nobody can stop decentralized voting. And we will. There is a secret project we're working on right now, which will just prove how impossible it is to block, actually, anything. And it's coming. Decentralized governance is coming on a global scale. You won't believe, and that no need for any adoption by any governments. It will happen by itself.
Yes, and I like the fact that technology itself already exists, but the coming to reaching an agreement is a much bigger challenge for humanity. And the last question, is it a layer 1 or layer 2 solution?
Okay, that's an excellent question, which just doesn't make any sense. Okay, the it's both. Okay, the borders are blurred, because what is layer 2 really? Like, okay, you can in a strict condition, like layer 2 is just an aggregation of layer 1 transactions. But if you can prove to layer 1 that your layer 2 has its own state, and you can prove all the state transitions, then can you kind of prove? Okay, so you prove that your layer 1 is actually proved on another layer 1 that it's layer 2. Okay, so there is no real difference if you can construct it in the correct way. And Gosh is doing this gradually, not yet there, but we released the first layer 2 proof system with Ethereum, between Ethereum and Gosh. We're going to do that between Gosh and Solana in the future, Gosh and Bitcoin, talking about that now. And then it will be coming, the Validium proofs coming there, and then it's it. It will be, the Gosh will be layer 2 to Ethereum, Solana, Bitcoin, any other network, bring it on. And if you want, vice versa, it's kind of just a question of proofs. There are algorithms, there are protocols there like Avail that provide you already, like now, universal layers of these proof systems between different blockchains. It's coming. So yeah, it's completely blurred. It's both.
Okay, and let me double check if we have any other questions from both live chats where we are streaming it right now. And it seems to be the last question for now. And it's been 1 hour since we started the live stream. Okay, then I think it's time to conclude our today's session. And thank you so much, Eugene. Thank you, Mitya, for delivering such a good presentation. And I hope this tradition will be we'll keep on with this tradition and see each other from time to time. And thank you everyone who joined this live session, or if you're watching this on YouTube, just leave your questions in the comment section. And after we publish this recording, I can also collect some questions from the comments part and address them directly to Mitya and Eugene. I think that's it for today. Thank you once again. Stay tuned. Bye bye, everyone.
Thank you. Bye bye.
Very much. Bye bye.